We are temporarily skipping matrices for one more video. Not because matrices are bad, but because introducing them too early is how innocent notation becomes a fog machine. Today we define invertible linear maps, prove the main characterization, prove the dimension test for isomorphism, and then come back to maps from V to itself. Let T be a linear map from V to W. We call T invertible if there exists a linear map S from W back to V. The compositions must give the identity maps. ST is the identity on V, and TS is the identity on W. That map S is called the inverse of T. It undoes T from both sides. Because half an undo button is just another machine for disappointment. If an inverse exists, it is unique. Suppose S and S prime are both inverses of T. Then S equals S times the identity on W. Replace that identity with TS prime, and use associativity of composition. So S equals S prime. The inverse is unique, and we denote it by T inverse. Now the first main theorem. A linear map is invertible if and only if it is injective and surjective. At first this may look like a fancy way to say bijective functions have inverses. But the important point is stronger. The inverse map is not just a function. It is linear. That is the part doing actual mathematical work. Otherwise this theorem would be wearing a suit to say water is wet. First suppose T is invertible with inverse S. For injectivity, if T of U equals T of V, apply S to both sides. Since ST is the identity, U equals V. For surjectivity, take any W in W, let V equal S of W. Then T of V equals TS of W, which is W. So invertible linear maps are injective and surjective. The undo button actually undoes things. Stunning. Now suppose T is injective and surjective. As a function, T has an inverse S, but we still need to prove S is linear. Take vectors W1 and W2 in W, and scalars A and B. Let V1 be S of W1, and let V2 be S of W2. By linearity of T, T of AV1 plus BV2 equals AW1 plus BW2. Apply the inverse S. We get S of AW1 plus BW2 equals AS of W1 plus BS of W2. So S is linear. Therefore a bijective linear map is invertible as a linear map, not just as a naked function wandering the streets. Now we define isomorphic vector spaces. Two vector spaces are called isomorphic if there is an invertible linear map between them. For finite-dimensional vector spaces, being isomorphic is equivalent to having the same dimension. So dimension completely classifies finite-dimensional vector spaces up to isomorphism. The spaces may wear different costumes, but they have the same skeleton. First, suppose V and W are isomorphic. Let T be an invertible linear map from V to W. Then T is injective and surjective, so null T is just 0 and range T is all of W. Rank nullity gives dimension V equals 0 plus dimension W. For the other direction, suppose V and W have the same finite dimension. Choose a basis V1 through Vn of V, and a basis W1 through Wn of W. Define T by sending A1V1 plus through AnVn to A1W1 plus through AnWn. Because coordinates in a basis are unique, this map is well defined and linear. It hits every vector in W, and only the zero vector of V maps to 0. So it is surjective and injective, hence invertible. There are some matrix-related results nearby in the usual development. We skip them for now because we have not defined matrices yet. This is not avoidance. This is sequencing, a rare moment where pedagogy defeats chaos. Now L of V means L of V, V, the linear maps from V to itself. For finite dimensional V and T in L of V, the following are equivalent: invertible, injective, and surjective. Rank nullity says dimension V equals dimension null T plus dimension range T. If T is injective, then null T is just 0, so the range has dimension equal to dimension V. Since the range is a subspace of V with the same dimension as V, the range is all of V. Hence T is surjective. Conversely, if T is surjective, then the range is all of V. Rank nullity then forces null T to have dimension 0, so T is injective. Finally, invertible is equivalent to injective and surjective by the earlier characterization. All three conditions are equivalent. Let us summarize before matrices finally enter the room and start rearranging furniture. An invertible linear map is a linear map with a linear inverse. A linear map is invertible exactly when it is injective and surjective. Finite dimensional vector spaces are isomorphic exactly when they have the same dimension. For a linear map from V to itself, injective, surjective, and invertible all become equivalent. Next time, matrices begin. At long last, the rectangular arrays of numbers get their dramatic entrance.